Now I know I'm stating the obvious when I say this, but testing the code that you write is very important. You obviously want to make sure that what you're coding is producing the right output. And this is where unit testing in Python comes into play. Unit testing is a way of ascertaining whether a piece of code that you develop performs the intended operation in the way that you designed it to work. Now this piece of code may be a full module, it may be a function, it could be an interface. It is essentially a piece of code that you've written. Now usually unit testing is performed by the developers themselves to ensure that any error that crops up whilst developing is resolved before it's then passed on to the next level, which is known as integrated testing. But integrated testing is outside the scope of this course, seeing as we're developing programs, we're more interested in the unit testing aspect. Now Python allows us to automate the testing process, which enables developers to do the testing in a very short time period, and the tests can be repeated. So let's dive in to see how unit testing works in Python. So let's just say we've created a simple line of code, and we now want to test whether this code is performing as we expect. We obviously want to make sure there's no bug in the program, and we want to make sure that it works in different scenarios, because we're not quite sure how an end user will interact with our program. They can input unexpected things. Now Python developers can obviously test their code manually, but doing it manually will obviously take some time. You may find that the tests are done on the fly and they're actually not documented very well, and if you needed to repeat the tests, you'd have to go back and once again do it manually, so it's very hard to maintain. And this is why it's encouraged that developers create scripts that can then be used in future testing, i.e. the testing can be repeated. And the way we do this is by leveraging what is known as a unit testing framework, which is handled within the unit test library, and just makes automating testing very simple. So let's run through some examples. Let's suppose that we create a very simple program, and to do this I'm first of all going to import the math module, and then secondly I'm going to define a function which calculates the square root. So I'm going to call this function square_root, and the intention of this function is to simply calculate the square root of the number that's provided into the function. So inside parentheses I'll create a parameter called num. I will then put a colon. This function will then return math.sqrt, so we're going to access the square root method from the math module, and we're going to pass into the parentheses num. So if we run this code cell and then test to see if our square root function is performing as we expect, we could put square_root and then pass into parentheses 25. In our minds we know this should be 5, and when I run this code cell we do get 5. So we know just by looking at this in a manual way that our unit of code, i.e. this function, is functioning correctly. But would it work all the time? Well, let's now start thinking of some test cases to ensure that it does. So I'll first of all just print a simple sentence that says the square root of 49 is, I can then put a comma, and I'm then going to concatenate a call on the square root function and pass in 49. When I run this code cell, you can see that we print the square root of 49 is 7. Great, so test case 1 has passed. Let's do test case 2. Let's now print the square root of 5 is, and then we're going to call upon the square root function, and we're going to pass in 5 in double quotes. You can see that when I run this code cell, test case 2 fails. We run into a type error, and we're told that it must be a real number, not a string. So seeing as this test case has failed, we know that we're going to need to add some control in our code to ensure that the input from the user is not a string. And like we've seen earlier in this section, this can be done by exception handling. So that's the first way we can do some tests. It's very manual, but we'd be able to run these code cells to see if we run into any errors accordingly. Now taking things one step further, I could also use the comparison operator. So I could put square_root brackets 100 equals 10. And you can see here that we bring back true. If I were to change 10 to 11, you can see that we bring back false. But the code cell still runs without any error, even though it's producing a false Boolean result. Now, a way that we can get the Python interpreter to throw an error is by using the assert statement. So we could put assert and then call upon the square underscore root function, pass in 100 and set this equal to 10. I could then put a comma and then I can put a string that we'd like to see if this condition is not met. So let's simply put the result should be 10. Now when I run this code cell, you can see that we don't run into an error. So if we had 20 of these assert statements and it run through each one of them individually, if it got to the end without any error, you know that the test cases have passed. However, if a test case doesn't pass, for example, if I put assert and then put square underscore root brackets 25 equals 6, and then put a comma, and the message that we get thrown back is the result should be 5. You can see that when I run this code cell, we run into an assertion error, and we're told the result should be 5. So we'd need to go back and take a look at one of two things. Is our function operating correctly, or is the value that we're testing against incorrect? In this case, we can see that we're testing against the number 6, someone's typed that incorrectly, so if we change this to a 5 and then rerun this code cell, you can see that we no longer run into that assertion error. So we can get the interpreter to throw an error, which we'd then need to investigate, and it would help to see if the units that we've coded are operating as per expectation. Moving on and taking it one step even further, we can put our assert statements inside of a function. So let's call this function test underscore sqrt. We can then put parentheses and a colon, and we can then just have all of our assert statements inside this function, which are called upon one by one. So let's first put assert square underscore root brackets 64 equals 8. We could then put a comma, and we could then have the message the result should be 8, which would be returned to the screen if this does not hold true. We can copy and paste this code line, and then we can have square underscore root 81 equals 9, and the result should be 9. And finally, if we copy and paste it one more time, we can put square root brackets 100 equals 10, and then the message can be the result should be 10. Now, if this was the only function definition in our code file, at the bottom we could put something like if dunder name dunder is equal to the string dunder main dunder, and we saw what this means earlier. It means that the following code will then execute if we're running this code file directly. We can then call upon the test underscore square root function, and we can then print everything passed. So if after running this code cell everything is passed, we will print to the screen everything passed. So we can gain comfort that our function is operating as per expectation. So you can see if I run this code cell, we do indeed get printed to the screen everything passed. Now let's slightly tweak the function so it doesn't perform as per expectation. Let's go back up to where we define the square root function, and where we return math.squareroot brackets num, we're going to add a -1 to the end of this statement. If I rerun this code cell and go back and rerun the test underscore square root function and then run the if name equals main code cell, you can see that we run into an assertion error. It tells us that the error occurs at the point where test underscore square root is executed, and then we're told within this function the assert statement square underscore root bracket 64 equals 8 has some form of error in it, with the assertion error telling us the result should be 8. So once again, one of two things can happen. Maybe the value that we're comparing it to is wrong, but here you can see we've actually put 8, so this test condition is correct. So this would mean we'd need to go up to our function to see what's going wrong. Okay, I can see the developer has put -1, so let's remove -1 from this function. And if I go back and rerun if name equals main code cell, you can see that we get everything passed. Now we can obviously include as many assert statements as we like, but here you can see that all of our test cases are executed under name equals main condition. So this would only be executed if we're running it directly and not importing this module into another code file. But once again, there is a shortfall with this, we don't get a very comprehensive test result of how many tests have failed. Essentially what we get here is that when there is a specific assert statement that runs into an assertion error, the script will stop running. So is there an even better way to do this? Well, this is where test runners can really help. Test runners can provide us an easy way to execute many test cases, and it will also publish a clear result of how many tests have passed and how many tests have failed, which is obviously great to keep for audit purposes. And the unit test library is one of these inbuilt test runners within Python. So let me show you how this works with two examples. Firstly, I'm going to go into Visual Studio Code and create a new Python file called unit_test.py. And this file will simply import math. We will also import the unit test library, and notice here that it's unit test as one word. And then we're going to define our function called square_root, and we're going to have num as a parameter. And we're then going to return math.sqrt (num), which is what we did in the Jupyter Notebook. Now, the reason the unit test library is so powerful is because it allows us to use a variety of assert methods, as opposed to just a simple assert statement like we've seen in the prior examples. And to set this up, we need to define a test class. So for the purposes of this example, I'm first of all going to put class, and I'm going to call this test class test class for simplicity. And this test class should be created by inheriting the test case class from the unit test library. So in brackets, I need to put unit test dot and then call upon the test case class. What we can then do is define our test cases. So I can put def test_case1 and then pass in the self keyword. I can then put a colon. I'm going to put self dot and then I'm going to call upon the assert equal method, which is very similar to what we performed in the previous examples. The first argument will be the function that we're testing, so we can put square_root and we'll pass in 121 inside parentheses. We can put a comma. The second argument will pertain to the value that we expect this result to be, in this case 11. And then the third parameter will be the message that we want printed to the screen if this test case fails. So I'll put the result should be 11. I'm then going to copy and paste this test, and I'm going to create test case 2, where the square root of 144 should equal 12, and then I'll change the message to be 12. I'll do the same for test case 3, where the square root of 169 should be 13. Test case 4, where the square root of 196 should be 14. We can do test case 5, where the square root of 225 should be 15. And finally, we'll do one more test case 6, where the square root of 256 should be 16. At the end of this code file, I'm going to put if dunder name dunder equals dunder main dunder. I can then put a colon, and then I'm going to execute unit test.main. So if I now go into Anaconda prompt and navigate to the folder where this code file is saved, and then put python unit_test.py, you can see that we get a result that says ran 6 tests in 0.002 seconds, OK. Fantastic, so there's no error with this specific file. What would this report look like if there was an error? Well, for this example, let's just quickly change test case 6, where we expect the function's result to equal 17. Obviously, this is a wrong input, but it will demonstrate how the report of the unit test library changes. So you can see that if I rerun this code file, we get presented with the message fail test_case 6. It tells us that the assertion error 16 does not equal 17, it should be 16. It ran 6 tests in total in 0.004 seconds, and 1 test case failed. If there were 2 or 3 that failed, you would see this result accordingly. So you get a lot more information by using the unit test library than you did previously when simply creating individual assert statements. And because I feel unit testing is so important for any developer, even if you're just starting out, it's important to gain an appreciation of testing best practices, I'm going to run through one more example. So let's create a new code file, and we'll call this code file my_script.py. This code file will have two functions. We'll first of all define a function called cap_upper, and we'll pass in one parameter labeled text. This function will simply return text.upper. So it's just going to capitalize the input that's passed into text. The second function will have one called def_adder, and then we'll pass in two parameters x and y. And this function will simply return the summation of x plus y. But let's just assume that the person who defined this function accidentally added -1 to the end of it. We can then save this code file, and we'll assume that developer A has created it in isolation. Developer B comes along and is asked to test developer A's work. So we'll create another code file called test_my_script, and this code file will first of all import the unit test library, and secondly, we're going to import developer A's script, which we know is my_script. We can then create our test class, so we can put class test_upper_add. Inside parentheses, we're going to then inherit from the test case class, which is from the unit test library, so unittest.testcase. We can then put a colon, and the first test that we're going to do is just test the cap_upper function. So we'll create a function called test_1_word, and we'll pass in self. We'll then put a colon. We'll have some text, which equals the lower string Python, and we'll set the result to equal a call on the cap_upper function from the my_script module. So we can put my_script.cap_upper, and then we can pass in the variable text which we've written above. We can then put self dot and then call upon the assert equal method, and this will compare two things. It will first of all take the variable result, which is a call upon developer A's cap_upper function, and the second argument will be the expected result from this test case, which we know is Python in all capital letters. So this will be our first test. We'll create a second test, and we'll call this test test_multiple_words. We'll then pass in self. The text will equal Monty space Python, and the result will be a call on the cap_upper function from my_script once again. We can then put self.assert equal, we'll pass in result, and the result should be Monty Python in all capital letters. Now we haven't tested the adder function yet, so let's now create a test called test_adder, which passes in self. We'll then set variable x to equal 5, variable y to equal 10. We'll set the result from a call on our function to be my_script.adder, where we pass in variable x and variable y. And then we want to self.assert equal and pass in the result and compare this to the number 15, because we know 5 plus 10 equals 15. Once again, at the bottom of our testing script, we can put if dunder name dunder equals dunder main dunder, then we call upon unittest.main with parentheses. If I go back to the Anaconda prompt and call upon test_my_script, you can see that we're presented with a failed test case, test_adder, and we're told that the assertion error is stating 14 does not equal 15. It ran 3 tests in total and 1 failed. So why is this? When we look at our assert equal statement, we are expecting the result to equal 15. So something must be wrong with developer A's code file. So let's go back to the my_script code file. And okay, we've spotted the issue. They've added -1 accidentally. So let's now correct this code. We can resave the code file, rerun the test script, And now we print ran 3 tests in 0.001 seconds. Okay, no tests have failed. Fantastic. We were easily able to rerun all of our tests that we created after changing the main code file. So very easy to repeat this action. Now so far we've only used the assert equal method, which tests to see if something equals something else. But we do have other assert methods available in Python. For example, if I go back to Jupyter Notebook and import the unit test library, and then put unittest.testcase. And then press tab, you can see that we have other assert methods like assert almost equal, we have assert equal that we've seen, we have assert in, which will check to see if the result is in a sequence that you provide, for example. We have assert is not, and so on. So there are a lot more assert statements that you can utilize when using the unit test library. Now there are more test runners you can use apart from the built-in unit test tool. For example, there is PyTest and something called Testify, which I believe is very similar to PyTest. But if you're comfortable using the unit test library, then I would suggest exploring this one first before moving on. So to quickly summarize, unit testing is very important to ensure that your code is operating the way you expect it to. When you change code, you don't want to repeat the testing by manually performing it every time. A way to get around this is to automate your testing so it's repeatable, and this can be done using the unit test library.